All right, welcome back. For our famous next session, I'm reliably informed you can't change the laws of physics, but our next speaker has learned how to bend them a little bit. So I'd like you to please welcome to stage the Chief Technology Officer of Metamaterial, an expert in holographic, lithographic nanomaterials for photonics, Jonathan Waldron. Thanks, John.
I'm actually not a very good public speaker. I tend to forget everything, whether it's the content, whether it's the dates, whether it's the people's names. So I wanted to start my presentation by going back in time a little bit to a couple of years ago when I looked towards my AR glasses to help me out in another very important family presentation, which I think you could all relate to and sympathize to a certain extent. So, for those that don't know me, I'm Jonathan. You can put the sound up. My wife, Lindsay, and I would love to thank you so much for making this so special. What a fantastic setting for a celebration. And what a beautiful ceremony. You may not know, but my wife was a fashion designer. So I thought I would make my speech like that of a well-known item of fashion clothing, the miniskirt. Short enough to be interesting, but long enough to cover the essentials. And so that's what I aim to do this afternoon, cover the essentials about Meta, our company. We are fundamentally a materials company, a metamaterials company. And in so, as it applies to AR, we're developing revolutionary new embedded materials technology that goes actually inside the AR lens. So you probably couldn't get as deep a hard tech for hardware in AR displays as what we're doing. So in this talk, I want to explain about how, despite a multiplicity of different platforms that we have, we've actually combined two platforms. A metamaterials platform where we can embed new functionality that is totally invisible, totally transparent in the lens itself. And then secondly, a new methodology for making lenses, prescription lenses. So every pair of glasses that we actually develop are indeed glasses that are prescription glasses, or ophthalmic eyewear. So I'll describe how a range of these specific functions can be serving all the salient requirements of next-generation AR glasses, which is where we're aiming at. So metamaterials are complex structures. They are applied on plastics or metals in ways that perform a very special function. And at Meta, we design and develop these metamaterials really to integrate the functionality, as I mentioned, in whatever aspect of the glasses are needing that, from functionality, which I'll come on to describe and show examples of, right through ultimately to meta lenses themselves to reduce the size of the projection displays in use today. But we go beyond in that sense because we also develop the manufacturing processes where we can reduce the price to a level that makes them extremely feasible. And in the past, if you've ever been interested in metamaterials, you've always seen very much a lab and fab-based scale process where these types of technologies have not been affordable. That's different with us. We actually have roll-to-roll processes up and operational with these metamaterials today. So as a company, we're a little bit different insofar as we have a worldwide presence, and alongside these manufacturing processes, we've invested very heavily in manufacturing infrastructure. And in that respect, we have over 200,000 square feet split between our two Canadian facilities, one in Thurso, one in Nova Scotia, and another 50,000 square feet based in Silicon Valley, where I'm from. So we're very interested in working together with OEMs or other companies with bringing these products to fruition, where we provide, if you like, a tier manufacturing service for the critical components such as the lens that might be incorporated into these products. These are some of the engineers and product managers who have allowed us to use their brand that we've been working with in the past and today, and it's a burgeoning area in that respect. Some of the key challenges for AR glasses, which is one of the reasons we haven't seen them come to market yet in mass market form, is all the different plethora of requirements that people have with respect to wearing those glasses all day. Whether it's from reduction of eyeglow, whether it's from a bright, efficient display that doesn't need, that can literally be all day wearable, and doesn't need permanently to be attached or tethered to something. So it's really a very complex balance of systems integration to achieve a device like that. So rather like, you know, in the early days of cell phones, looking forward 10 years, what does it take to achieve that critical mass? And we believe that it begins and ends with the material science embedded in those glasses, and this is the class of technology that we're bringing through at Metamaterials, very focused on that. The goal is to make these AR glasses very comfortable, all-day wearable, as I mentioned earlier, and I look at it rather like the Apple Watch. You know, to begin with, it was kind of marginal, the functionality embedded in it, but now today, it's become a very compelling device with proper all your music or radio antenna, connection to the web, connection obviously to your cellular distribution, so it can receive calls in isolation. So it's really evolved as a category of device, and we think the glasses certainly will do the same, no question. So once again, I mentioned earlier that I'm going to concentrate on just two of our meta platforms, if you like, our NanoWeb and our proprietary ARfusion platforms, making the ophthalmic glasses and lenses. In terms of NanoWeb, this is our first electro-optical platform technology and really delivers quite revolutionary new capability, electro-optic capability in its own right. Basically, NanoWeb is a sub-micron and nanometer scale metal mesh that we can pattern in any different way. Think of it like a highly integrated circuit, but it's down at the 200 nanometer level. And the importance of that is it's not being made in a fab. It's being made roll-to-roll lithography, which I'll come on to. It has extremely good electrical conductivity, about only 1 ohm per square in terms of resistance. And this has a knock-on effect to reducing the power consumption needed for many of the applications that we're addressing embedded in the actual lenses. It's quite different from ITO, which, as you know, is a very rarefied material, increasingly so, cannot be patterned anywhere close to this sort of level, and even if it was, is a very expensive process, is difficult to get onto curved, preformed plastic substrates for reasons of breaking up, etc. So we're really quite different in terms of our metal mesh being a conductive platform there. And I mentioned earlier that not only do we have this very low sheet resistance of around 1 ohm per square, but critically also up to 99% transparent. You cannot see these structures at this level, impossible. So when it's fully embedded in the lens, it's completely transparent. Very difficult to see. So manufacturing today, just very quickly, we have a multi-step process. We already have our roll-to-roll line for NanoWeb fully operational now and producing parts for customers. This will grow in terms of its width and in terms of its speed, collapsing the price as we go forward in that respect. And it begins by taking a plastic sheet, coating it with resist, adding then the first step, that roll where we're exposing it with these nanoscale structures using our rolling mask lithography process step. We then fix it through a baking step. We then develop it, which creates the tiny little nano 3D structures in that resist that then allows us to metallize it by using it in a standard e-beam metallization tool that we've developed. And this is a critical step to laying down the nanoweb or the patterning inside of the lens. We're also very advanced in developing new types of metallization capability. Here we call this the virtual cathode deposition. And this is a remarkable new type of metal deposition that we're actually developing at Meta so that we can increase the speed of the roll-to-roll process step. This is beyond a classical e-beam methodology and once again called virtual cathode deposition. And just to demonstrate this quickly, you can see here a plastic golf ball. We can actually, using VCD, deposit nearly 100 nanometers of stainless steel on this demo golf ball very, very quickly. And this is a low temperature deposition process, so it means that we can have very, very thin plastic substrates to create our nanoweb materials. So once we have that metallized, we do a standard lift-off process and removal of unwanted materials, which we then recycle after that. So the second platform combined with this, we call ARfusion. And here we've developed a roboticized process for creating prescription lenses. Why do we need to create prescription lenses using a filled cavity of monomer to actually cast the lenses? The reason is during that process, we can fit in these metamaterial films inside to, which I'll come on to explain, do a whole variety of transparent functions. You can see here it's the lens, the two glass cast lens pieces are filled up with monomer. It then goes in for UV curing. Then the robot takes it out and with that cast lens splits the mold to create the lens structures to your prescription. This is all very, also very environmentally friendly because we don't have a lot of the post-polishing steps, which is very typical for lenses. The lens comes out ready to use straight away. The other critical aspect is it ends up with a lens that not only can have a lot of capacity through the system, but critically is very inexpensive. In fact, it's at a parity with conventional lenses in that respect, notwithstanding that we functionalize it with different capabilities. So these UV cured acrylic lenses made by Meta, today we have about 2,000 molds, all the different prescriptions that you might imagine necessary to satisfy a whole user base. And with the, as I say, the less energy we use in the finishing, it makes it extremely cost effective. We've developed a unique process then where we can encapsulate, let me give you a couple examples, an embedded filter, for example. You always see with HoloLens that eye glow from the front of the HoloLens where it's lit up. Nobody wants to wear AR glasses like that. So we have to shield the reflection of that projection energy into the eye, and this is one of the things we can do with our films, is have a total shield for that particular band of light that's going forward. So reduction of eye glow, or another application is electrochromic dimming. When I walk outside and it's a bright sunny day, I don't want to have to spend all the energy resources in the glasses to try and contend with an extremely bright environment. Far easier just to dim it down. And so I'll come on to show you our electrochromic dimming capabilities. So all of these functions, whether it's a set of tiny miniature cameras that we can place for eye tracking, or it's some of these sensor films or holographic films, these are all capabilities that we've developed so we can embed it in the lens. This gives you the holographic display, the electrochromic lenses, laser glare protection, as I just mentioned, are all functions that can be embedded in there totally transparently in that respect. And in terms of the see-through capability, again, ophthalmic lenses, ophthalmic glasses have a very high requirement for transparency. We can meet that requirement with nanoweb because the structures are just so tiny. It reduces any form of haze and gives you very good transparency in that respect. We've also embedded gratings in there so that you can have two-axis pupil expansion embedded in the lens as well, So again, has the flexibility not just for holographic classical combiner type arrays. These are some of the examples of the cameras that we've embedded. These are more experimental ones. They don't have to be seen in the actual lens, and these are used primarily for eye tracking. We've also developed waveguide eye tracking as well. Here's an example. If you go to work and you're wearing a mask and you have an inequality of ambient heat such that you then, with that differential, get a fog building up on your lenses, this is a problem for everybody, especially in this mask-wearing society today. So whether you're a chemist trying to do your work, we can put in a nanoweb film that literally heats, and with that mild heating, disperses that. So whether you're a skier not wanting to have foggy glasses, or whether you're a chemist at work not wanting to have foggy glasses, or using AR, in all cases, this is a clear application for our nanoweb embedded in the actual lens with regard to that. So with this, and given that the sheet resistance is just so low, we attain a new level of efficiency with that heating capability far beyond what we've seen from ITO in previous examples in the past. And that leads to this all-day wearability capability that we need to see. Another example is in electrochromic dimming. When we go outside, move into the high ambient air, we don't want to have to build the bulk and the power requirement to overcome that ambient light. So simple electrochromic dimming not only gives you a lens that can electrochromically dim down dynamically and has fast response rate. This is all driven, by the way, at 1 volt. So it's very tiny power consumption, and also makes for a very nice pair of dynamic, tunable, dimmable sunglasses. And this is what we need from AR glasses, is not just the capability for obviously display and to be tethered and to provide all the exciting opportunities with content, but critically also be an extremely functional pair of glasses that has a multiplicity of different functions, whether it's reading off a script, as we started with, right through to actually having the capability to dim down. So again, one of the things we announced a couple of months ago is using nanoweb to print literally an antenna, a receiver, in the lens itself. And in so doing, what we've done is to make it completely transparent, a high band, 32 gigahertz, high band 5G receiver. Why in the lens? Because it's a very large area. It's ideal to pick up signals in both sides of the eye. It costs you nothing in terms of throughput because it's totally transparent, and gives you the opportunity then to change the system's integration away from having all of the computation of the imagery and the interaction done on board, but have it off-boarded to a localized transmitter in that respect. And we think that that can give systems integrators a lot of new flexibility and opportunity, once again, to get down to that Warby Parker size and structure. And there, if you actually see the lens itself right up, I challenge you, if you ever could point it out. It's impossible to see, so totally transparent in that respect. So we think Meta provides a really broad technology platform portfolio, and our metamaterial cast lenses solutions can help deliver the challenging technology needed for truly embedded glasses with the functionality embedded before. And previously, over the last 10 years, this has always been an accumulation of different systems added together, creating the bulk and the headsets to get down to this level of glasses and a device that is truly of that size and that class. We must integrate new physics and new technology into the lens itself, and with this platform, we think that we have a good chance of doing that. And we've combined, as a materials company, along with Corvestro of Germany and also PPG. PPG were the inventors of transitions. This is a photochromic technology, which you know they then sold to SLR, but now we're the chosen partner for electrochromic dimming for these types of devices. So together with Corvestro and PPG, we've formed a partnership which we call a one-stop shop, where we can offer all these technology solutions to OEMs looking to bring glasses-like product to market using this sort of level of technology. So the one-stop shop is really for the industry collective in that respect. So finally, we think this is an important step forward. Metamaterials have a hugely important role to play to take us to that next generation. We're hoping that it's enough to create that all-day wearability and a sufficiency of display and other ancillary capabilities in the device to create a really seamless experience for the user in that respect. So thank you very much, and I've got a couple of minutes if anybody has any questions at all. Thank you. Is there any questions? Okay. All right, I think I'm good. Thank you very much. Thank you. Okay. Sure.
We had a quick chat behind the mysterious curtain on the stage, and he told me that he was the founder of the company of my very first VR experience 25 years ago, which was just a thrill. So that's what happens at all. You get some incredible veterans with some amazing experience. So make sure you grab this gentleman. He's got some great stories. We're going to have the next session in just a minute. I would advise you to keep in your seats. You're not going to want to miss this one. I'll be back with you in 30 to 60 seconds.